So this will be the about the quiz. I guess it's quiz 6, chapter 7. So the first one we're going to look at here is going to be this table here. That's getting into the two-way table situation here. And one thing is this is going to pop up, and like if you're working, it might be hard to move it around. So you might try using the snipping tool. That way you can have it on the side over here while you're working on the problem. That's just one way. It helps that way you can, because that's what anyway, you can set it up like that, right? So what we've got to do here, and this can be a little confusing, notice that we have a table here as two separate tables, one for men, right? One for men and one for women. We want to put it into a format like this where we have all the men over here. So what that would require would be to add up all of the men who are for capital punishment, and that would be 7 plus 12, and we got a 19. So see, that would go right here, right? And I'm just doing part A here where it was asking us to make the two-way table based upon this data. So then we'll read the problem more clearly what they're asking. So that's the first step. And then what we want to do the same thing, is add up all the men who are against capital punishment. As you can see, that would be 8 plus 3 right here, right? 8 plus 3, and that would go in this column right here. And then do the same thing with the women, 2 plus 5. And we got a 7, that's for capital punishment. And then 8 plus 5, that's against. So the 4 would be a 7, and then the against would be a 13. Hopefully I got that set up right as I'm moving around stuff. One thing to think about is I see students say, well, they can't do this because notice it's the essence of this problem, and I put an instructor's note in here to explain what is being. Let's just check this first. See, we got it set up right. So here's the what's a little bit confusing about this problem, and one is, hey, well, you got more men than women, you can't do this study. Well, we have a proportion, and based upon our sample size, we'll assume everything is met as far as that goes. But anyway, we can do that because we still have the same proportions. Sometimes you'd have to make that accommodation based upon availability. So, but here's the idea of what persuasion is. Just think of persuasion as a treatment. So here it is. The student who collected her data could have made the results misleading by trying persuasion more often on one gender than the other, but she did it on the 10 out of the 20 women and 15 out of the 30 women. So there's 30 men, right? That's what I was getting to. That's fine as you got an equal proportion and you're equally distributing your treatment. So the non-persuasion ones would be a half of those. So what she was doing is this, I guess she did do something. She broke them up into groups, those that getting persuasion and those that are not. It's a little hard to see because we don't know all of the details, but we can see that is what that is a treatment, and it should be. That's how we should treat it. It can be confusing. I did put an instructor note into this one explaining that, so you can see what's going on there. So now, of the 30 men sampled, so we're only talking about men. See this? Of the 30 men, what percentage supported capital punishment? And what we're talking about here, we already know that it's out of the 30 men. How many supported capital punishment? That's 19. And it wants a percentage, as we can see, so we need to multiply it by 100. And then it says 1 decimal place as needed, so it should be 63.3. And then of the females, remember that this is going to be out of 20. It's going to be out of 20. And there's 7 who are supporting capital punishment, and it wants a percentage, so we multiply it by 100, so that would be 35. Let's check our answer. So far, so good. So on the basis of these results, a jury of women would be preferable, right? Because a lower percentage of them are in favor. So as it says, if you were on a trial for murder, so if you're ever in this situation, I hope you're not, but if you are in that situation, especially in Texas, you would want, based upon these results, this sample, you would want a jury of women as opposed to men. Wait, what did I do? A jury of women be preferable as a lower percentage of them. Jury of as a higher percentage. Watch out for your negatives there. It says are not. Are not. There we go. There we go. So we'll go ahead and do this one, and I'm going to have to save it so that my old school computer doesn't crash. But anyway, according to a newspaper, 63% of high school students have a driver's license. Suppose we take notice this key word here, random sample. And also notice what's missing from some of the problems you saw with the symmetric normal curves given. One thing it doesn't say is symmetric and normal. So we have to assume that it isn't. So we would need to check and see if we can use the CLT here. So I'm going to stop this a moment so I can bring up the information that that will help you to work in Desmos. Work in Desmos on these things to make this whole thing a lot easier. As you work through these problems, you can assign variables over here, and then you can assign the variables over here, and then make it a lot easier where you don't have to keep recalculating. Well, let me see. Let me bring up the page here real quick. Okay, so in this question 2, what we have is a stepping ground into basically chapter 7. What separates it from chapter 6? Chapter 6 was the theoretical fantasy land of a normal curve, which one, we would have to know the population mean, the mu, and we'd also have to have the population standard deviation, the sigma, which is in most cases not realistic. It would require a census of everyone in the population. But anyway, we do have this newspaper that published this, and we can use this in our study since they've published this, and it will be based upon that, right? Based upon that. It's not, maybe if that's wrong, then our estimates in our sample would be wrong. But notice the key, what value should we expect for our sample proportion? I thought it was talking about the expected value, but notice it's talking about a sample proportion. But even though it says proportion, it wants it as a percent. So we got to be, I think the key on these is look out for that when it wants a percentage and when it wants a proportion, which would be just the decimal, not it converted into a percentage. But I wanted to establish, I want you to, yeah, I think you guys can do these problems a lot quicker because you're going to have some pretty complicated calculations if you set it up in Desmos, because Desmos will allow you to assign variables. So for example, remember n means the sample size, and as we can see up here, it's 200. We sampled, did a random sum. Notice also it says random. So that means we can use the standard error. We should check into the CLT if we're going to make any confidence interval concepts, but we can still make these values. Notice that n is the 200, and then let's go ahead and assign the proportion, or the population proportion. Even though it's from a newspaper, we're going to assume it's going to be the population proportion, which would be 0.68. So in our sample, we should expect that we should get 68%. Right? And you got to be careful. That's a weird, it doesn't really say what, anyway. That's what they're asking is out of the 200. And if what would we expect to have a driver's license? And then here's where it gets a little more complicated, and that's the standard error. And that's a fairly complicated formula that you don't want to be calculating over and over and over again. So that's what I'm suggesting, is doing these variable assignments. And then later I'll show you a formula sheet that I'll allow you to use. You can use anything, but I tried to simplify these because these are the more complicated formulas. So the way that I was assigning the standard error was S and then underscore E. Alright, so to get that E, you just hit the shift button and then you hit the button to the right of the 0, which is a line. And so there you have that, and then you just hit an arrow to get back out of it, and now you can assign the standard error. The standard error formula is the square root of the population proportion times its complement over the sample size. So there's our standard error calculated very easily. This will come in handy as we start getting into more complicated ones, where we start having to verify the conditions of the central limit theorem and also calculate a 95 or 90% confidence interval. So, but anyway, that's why this is going to come in handy, and we're just getting started. So the standard error, notice it doesn't have the percentage. Later on it'll want us to use the percentage because we'll use the standard error as sort of like a margin of error. So notice this one it wants put in as a 3298 as a decimal, and then notice it says to do rounded to 3 decimal places. So if we're going to do that, it would be tree. There we go. Now here's where it gets, again, we would expect this number 68, give or take, and then now we're going to convert this standard error into a percentage. And we really did just apply the central limit theorem on that estimate without checking if it conditions are met. But anyway, select the so now, and on the one, a lot of these, right, you got to read up here to understand what they're talking about down here. So suppose we increase the sample size from 200 to 400. What effect would this have on the standard error? So remember, what we have now is this value. Watch what happens when I increase it to 400. Notice that it went down to 2.3. So let's look at what they're saying. It will not remain the same. It will not increase. the standard error would decrease, and the new standard error as a percentage would be 2.3. Let's read this one. We cannot determine. Well, we just obviously determined it very easily by changing our value of n. So that's one way these variable assignments can speed up your work. Alright, so we're going to move on to the next one, but before we get to that, and it's got an instructor tip on it just so you can kind of see, and I think I put a page in the textbook that you can look up to actually see what they're talking about with this particular deck of cards. But anyway, before we get there, I want to show you something about Desmos. Okay, so once again I clicked on the screen, the graph, and then I copied it over into the snipping tool so I can work with it independently while I'm doing the problem. So this is a certain deck of cards that shows one of 5 different shapes. So the probability of selecting any shape would be 0.2. We could call that a success. A failure is, I guess, I think they ask you to guess, and then they turn the card around, and then it shows what the shape is. The subject knows what the 5 different shapes are. A great scene is from a movie, the original Ghostbusters movie, and you will see Dr. Beckman, played by Bill Murray, executing this experiment in a humorous way. So when we look at this, what it's asking, so the text graphs show a computer simulation of experiments in which a person was asked to guess which card had been selected. Each dot in the dot plots represents the proportion of successes of one person. Okay, one dot plot represents an experiment in which each person has 10 trials, another shows 20 trials, and a third shows 40 trials. When I had AI count them, I didn't get those numbers. I think I remember this the last time. But anyway, let's assume that the total number of dots are what I was able to count with AI. Let's just assume that number, and But anyway, let's just answer the question, and then I'll talk about what I assessed. Further analysis of what's happening here. But anyway, notice the spread. So remember when we were rolling dice and stuff, right? We had the law of large numbers, right? And the law of large numbers, right? And it was back and forth, right? And then it eventually started to converge towards the probability. If we're rolling dice, right, it would converge towards a half. So the probability of flipping, the empirical of flipping a heads or whatever would converge because of the law of large numbers. But notice the spread on each of these, and I'm going into that a little bit more than I wanted to. But anyway, let's go ahead and notice the spread here goes from 0 to 0.8. Notice the spread on graph. That was graph A, by the way. I just couldn't get it all in there. And then this is B. Notice the spread on this goes from 0 to, I guess, about 0.7, right? And then notice the spread on graph C goes from 0 to about, I guess, about 4.1 or something, I guess we could say. So notice as more dots or more samples of people, it starts to converge towards. See, it's starting to converge towards the theoretical probability, right? Which is 20. Starts to accumulate around it, and so that's again the law of large numbers. So graph C should have the largest sample size, and it tells us that, right? Let's see. Well, it just says another and another because it wants us to choose these. But anyway, the one with the largest sample size, and I did confirm this with AI, I counted, if you look in the old school, I counted them manually. So I'm not completely lazy. I did do it a couple times before. But anyway, graph, what is that? That's graph C would have the largest sample size because it has the narrowest width, the spread. And then A would have the smallest sample size because it has the widest width. Alright, so we got that. Now let's just think. I'm going to show you, before we go on to the next one, just an analysis of this binomial structure. And I had it's hard to explain without seeing things, so I had AI bring it into perspective for us. And remember the binomial structure we had, where we had the number of combinations of way these can occur, the probability of successes times the probability of failures, and then we had the R. I was using R, it's going to use K. And what we're looking, I'm just going to think, okay, what's the probability of a 0? And AI counted the dots, and there's actually, it said there's 22. You can verify this if you want. I have done it, and anyway. So the probability of a 0 would be 0.8 to the 22nd, right? Using the multiplication rule of independent events. So we have a fairly high probability for getting a 0. Again, because of that empirical probability that we had before, right? The law of large numbers. Right? And I put a half. It really should be, in this particular case, the probability that we're looking for is 1 out of 5, right? 1 out of 5. Because there's 5 possibilities. And that's what we had, which is 0.2, right? That's what we had before. So let's just think about the probability of getting it wrong. Probability of getting it absolutely wrong is right there when we do 22 trials, because eventually you're going to start getting some right? Wrong, like we have seen before, and then it smooths out, right? And then you can look over here. There's 4 zeros right here. And there's 1, and then there's 1 down here. And when you might say, well, if we did 4, why are we getting 4 here, then we're getting 1? Well, you got to think these are different trials, one thing. So we're doing it 20, and then we do another run of the 40 or whatever they have anyway. And so, as you can see, as we go on through here, now let's do the 30 trials. And notice how that's going up. It was 0.86% chance. Then as we increase the sample size, it's now a 0.006% chance of drawing a 0. And then as we go on up to 50, right? This is just what's going to happen when you start multiplying numbers less than 1 towards each other. They're going to get smaller. And as you can see, a large n, a 0, almost becomes impossible because we have a 0.2 probability, right? Anyway, that's the idea. Here's what it said. The zeros are not disappearing. These are separate trials. It's a different binomial model, and that's how we need to understand it. So I just wanted to put in some further insight into what's happening here. It's not, well, anyway, you get the idea. I just wanted to expand on that idea. So there we go. And so I was looking back, I started looking at question 4, and man, those looked exactly the same. And they are, right? and they are. Same graph, most spread on A, tighter. See, it says A is the largest. Only difference is it's talking about the standard error. So that's going to apply as well, right? There's less of a difference. So think of the standard error as the standard deviation, right? More variability, a higher standard deviation. But now we're talking about skewed data, right? That we want to get closer to there. But the standard error, remember, that is the correction to adjust what would be a skewed. And it is skewed, right? Because we have a 0.2 probability. But anyway, so start thinking about the standard error that we just calculated. The standard error of A has the largest standard error, and because it has the most spread, graph C has the least. So start thinking of it in that way as a standard error, not the binomial distribution, but those two things are connected for sure. So going on to question 5, I just want to do just a little peekaboo into the solutions on this. And then I'm going to show you the Desmos and where the formulas for setting up the Desmos that I recommend. You can do it however you want to. If you want to do it old school, you certainly can. Just remember, you're going to be timed on these tests. And you're going to be repeating the same calculations over and over again. So it does behoove you to use something that's going to save you some time. But anyway, here we have 70. So according to the article, 73% of high school seniors have a driver's license, which looks like what we just did. I think the only difference here is we're going to start really applying the central limit theorem instead of just assuming that it was by calculating the standard error. And we're going to use the standard error to make it in the normal curve here on this one. And the normal calculator in StatCrunch is the way that I'll do this. But we'll have a sample of 100 seniors, and we're going to find the proportion who have a driver's license, find the probability at more than 76. So here's where it gets different. We're going to find the probability that more than 76 have a driver's license. But before we can do that, we have to verify the conditions of the central limit theorem and for sample proportions. So that's where I'm going to turn over to explaining the Desmos stuff, and then we'll go through this one here without the answers. So hold on. So I want to show you a file that is in the week 6, and if you scroll on down here, you'll see this page, further insights on the central limit theorem here. So I just kind of explain why we have this. We'll talk about this maybe later, but right now I just want to start with this Desmos suggested population that we have here, and I have some key numbers that you should be able to copy and paste over into Desmos, and we'll test that out. I don't think this one will work. You have to type it in, but these critical values are going to be essential for when we get to the confidence levels, and definitely what we just saw before, sample proportion. While we're talking about this is a good thing to say that the sample proportion, I'm going to assign it P, but the sample proportion is actually P hat. P is the true probability, and P hat is like the sample the sample proportion. And we'll talk more about that. N is the sample size, and then capital N is the population size. And then down here you'll see the critical, a few, I should have arranged this, the CLT conditions, all three of these. One is the large sample, and that is that NP must be greater than 10, and N times its complement must also be greater than 10. And also the population, this is the big population one, and that your your sample should be less than 10%, less than or equal to 10% of the population. Why that is will be explained here. I'll do this as we go through each problem, and I'll expand that on out. But anyway, that's the basis. So now let's try to get what we have in this PDF file over into Desmos. Okay, so we have to start with a population proportion. We'll eventually assign those, and we will have to start with a sample size. We don't need to get to the critical values just yet, but I'm going to scroll on down to the bottom, and I'm going to show you an example of a problem. Now, let's go ahead and use this one right here. Well, no, let's just scroll down and look at what we have here laid out. So, right, and then we don't have our values yet. We're just putting them in. So, as I was saying, the standard error, and remember that is the square root for sample proportions, the proportion of success minus its complement over n. That will be the standard deviation. And then now to do this is the first part of the large number sample, which we know to be the expected value basically, and that should be greater than 10. The second part of the large sample is that n times its complement should also be greater than 10, so we'll verify that. And then to verify our big population, we need to verify that 0.5 times n is greater than, that our sample is no more than 0.10% of the n, or in other words, our sample should not be more than 10 times. Okay? So let's go ahead and put in a line for n. While it's not necessary in a lot of these here to do that, it's good for instruction to understand what they're asking, so you're just not getting used to flipping and saying, oh yes, it holds, and you'll know what I mean here in a moment. So now we understand what I'm going for here. There's some other ones here. When we start getting into confidence intervals, the z critical values, and also calculating the margin of error, and those others, we'll get to those here in a moment.